Now we will discuss about something known as centrifugal pump. Uh, Centrifugal pumps are radial flow machines, and the head duty pump is VU2, U2 minus VU1 into U1 by G. Now this can be maximum if this is 0, which means U1 cannot be 0, so U1 has to be 0, which means this is the velocity triangle at the inlet. This is V2, this is VU2, this has to be 0, which means the fluid has to enter the pump radially, right? Let me draw the pump. This is the impeller, okay? This is the direction of rotation, omega. This is the inlet velocity triangle, U1, so sorry, V1, W1, right? This is the outlet velocity triangle, U2, V2, W2. This is how the blades are arranged, right? This is beta 2, this is VR2, this is VU2, right? Now HP, this is 90 degree, it enters radially. VU2, U2 by G. VU2 can be written as U2 minus WU2. WU2 can be written as U2 minus VR2 cot beta 2. This is beta 2. Cot beta 2 is equals to WU2 by VR2. This is WU2. So HP is given by U2 square minus VR2 U2 cot beta 2 by G. Now U2 can be written as pi dn by 60, where d2 is this diameter of the blade tip, and VR2 can be written as pi d, which is the circumference, to b, which is the width. This is the area. If I draw, these are the impedance of the pump. If I see from this direction, This is the top view, right? This is the so this is B. This is area of exit. So we have VR2 equals to Q divided by so you have N D2 by dN by 60 whole square minus Q by pi dB it is HPE. Now we can see that this is a constant. We'll call this K1. This is another constant K2. And G will go inside these constants. So HPE equals to K1 minus K2 Q cot beta 2, right? So now we have pump characteristics. Pump characteristics is a graph between H and Q. From this equation, when we have three kinds of pumps depending upon beta 2. Beta 2 is the blade angle equals to 90 degree. When it is equals to 90 degrees, this is 0. So it's a straight line where this is K1, right? When beta 2 is less than 90 degrees, when it is less than 90 degrees, this is positive, and so the entire thing becomes negative. This is less than 90 degrees, and when beta 2 is greater than 90 degrees, this is negative, so this becomes positive. This is beta 2 greater than 90 degree. These are called forward curved veins. This is radial veins. This is backward curved veins. These veins are very commonly used in the pumps. This is direction rotation. These are the blades. This is beta 2 greater than 90 degree. These are radial blades where beta 2 equals to 90 degrees. These are backward curved veins, right? Now this part is very important. This is H, this is Q, this is ideal backward curved vein, right? Now this is impeller. This moves in this direction. Then we have positive pressure in this direction and negative in this direction. So positive in the front end of the blade and negative in the rear end of the blade. So flows happen like this. This is when a slip. This is a slip phenomena that happens. So this is U2, uh, sorry, V2 and W2. If this is the ideal case, because of slip, this is the actual triangle, right? You can see this is VU2 actual and this is VU2 ideal. So we have slip is VU2 actual by VU2 ideal, right? This is the slip. So head, so actual head will be this into HPE. So because of slip the head will decrease, so this distance will be 1 minus sigma HPE, right? We also know that there are losses. We will over here we will talk about two losses. One is shock loss. If the fluid enters, or this is W2, W1, obliquely to the direction of the blade, there is shock loss. Shock loss is HF. Shock can be defined as K3 into Q minus QD whole square, where QD is the design flow rate. Is not the design flow rate, is when W1 is along the blade, and that is the desired point. So this will be, this is after slip, this is the ideal one, this is the shock loss. Now the frictional loss will be KQ square, K4Q square. This will be like this. So the actual curve will look something of this sort. So this is this minus this minus this. This is the actual pump characteristics. If we try to draw it for this for backward, this will be for forward, this is for forward, this is radial, this is backward. Okay, power, if we see, this is, we can also plot power. These are power, these are plots for power. This is backward, this is radial, this is forward. Backward we can see that if this is operational point, anywhere below and above the operational point is at a lower uh, power. So if a load is suddenly increased and the flow rate decreases, the power will also decrease. In the reverse, the power will decrease. But here, if we in the forward, in the backward, in the radial case, if we try to run the pump over here, then we always have to provide a motor that is of a higher rating, which is costly. But here, if we buy a motor at this design condition, then any condition, be it higher or lower flow rates, the power will be less. This is known as self-limiting property of backward curve vane pump. Now when pumps are in series, let's say these are two characteristic lines of two different pumps. Okay, so when pumps are in series, resultant Q is equals to Q1 equals to Q2, H equals to H1 plus H2. So this is how pumps in series would look, where this is Q and this is H. The head gets added. So this is series. And in parallel, we have Q equals to Q1 plus Q2 and H equals to H1 equals to H2. So parallel will look something like this, where the Q is getting added and H this, sorry, not this. This is the graph for pumps in series and parallels. Another important thing, first we will draw the circuit over here. This is the pump. This is the suction line. This is the footbridge. This is the filter. These are the flanges, the bends. This is overhead tank. There is a delivery valve. These are again the bends. This is the pump. Okay. So from this side to this side, so this distance is known as static head. This is no static head, but the static head plus the losses is the manometric head. So Manometric head is the head developed by the pump. This is how it looks. If this is the head. This is at A, head at A. Now this is the entry loss. Okay. This is loss due to this height. Loss in suction line. This is the head developed by the pump. Now this is the loss in the delivery line. This is HF delivery line. This is the exit loss. Okay. This is the manometric head. And this is the static head. Okay. And this is point B. This is point A. Difference between A and B is the static head. So we have the system characteristics as K into Q square, because H system equals to H static plus the losses, and losses is defined by KQ square. Losses can be major or minor. Minor losses are in bends, valves, orifice, and major losses is friction loss in pipes. So we know that this is the HQ characteristics of the pump. HQ characteristics of pump. We can also draw the efficiency curve, which would look something like this, where this is the curve. This is the efficiency curve. This is the operating point. For max efficiency. This is not the operating point, but this is the design point. Design point for maximum efficiency, right? Now, from this equation, where H system is equals to H static plus KQ square, these are the losses. So if this is H static, so this is the HQ characteristics of the system. This is the operating point. This is very important.